Good afternoon. It's 1:30, so we can start our lecture today. What was the last thing we did the other time? Was it indices or logarithms or sets?
Indices.
Indices. Did we do logarithms?
No, sir.
No, sir.
No, we only did indices.
The laws.
I think the laws of indices.
Okay. After the laws, did we do some examples?
No.
We only did the laws.
Yes,
Yes,
please.
sir.
Okay.
Yes, sir.
Okay, good. So let's try and use the laws to work out some examples, and then we can move to what I want to do today. I wanted to be sure of the questions I solved with you. So let's take some indices questions, and then we can apply the laws. So I'm going in for more difficult questions, which can help us to apply a couple of the laws. I want to pick these questions here. Let me try and look for my marker. Okay, so I have my marker now. Good. So let's pick. I want to see whether we can solve these three examples. They look a bit scary, but we can solve them. H, I, and J. And then after that, we can move to the laws of logarithms. So the first one is 1 divided by square root of 25 to the power -1 times 4 square root of 16 to the power -1 divided by 5 square root of 4 to the power -1. Let's see how we can solve these questions using the laws of indices. So let me rewrite the question in a way we can all solve it together. I'll put them up here as follows. So the first one, we have 1 divided by square root of 25 to the power -1 multiplied by, no, let me write it well so that you can see. Let me come up. So 1 divided by square root.
This meeting is being recorded. This meeting is being recorded.
To the power -1 multiplied by 4 root of 16 to the power -1 divided by 5 multiplied by square root of 4 to the power -1. So let's use one of the laws which says that a raised to the power -m is the same as 1 divided by am.
It's the part.
Yes, so I need to mute all of you because I'm having some feedback, so I'm muting all of you. So we use this law to try and work out what we are seeing here. The -1, -1, -1, we are not comfortable with it, so we need to work it out with this law. And so this one will become 1 over square root like this, 25 to the power negative 1, when we are rewriting it with this law, it will become 1 over 25, like this. Multiplied by, then we have 4 also this way. And that will also become 1 over 16 divided by 5 square root. So 4 negative 1 will also become 1 over 4 this way. Then we can break them down as follows. So 1 divided by, then you are sharing the square root for them. Square root of 1 will give you 1. Divided by square root of 25 will give you 5. So you have 2 overs here now. Multiplied by, then you have 4. Then we look at this also. Square root of 1 is 1. Square root of 16 is 4. All divided by, then you have 5 here. Square root of 1 will give you 1 divided by square root of 4 will give you 2. So at least we've been able to clear the root signs in them. But we are having so many divisions. So division, I have 2 here. Then look at this side, we have 1, 2, 3 divisions. It's looking too clumsy, so we want to write it in a simple way. So we can rewrite this one as this one. I'll write it this way, 1. And then this division sign, we do it like this, divided by 1 over 5, this way. So at least we've cleared this one. Okay, as one bit like this. Multiplied by, then let's go to the side. This side we can see 4 will cancel itself 1. It will cancel this 4 also 1. So with that cancellation, we have reduced this one to become 1. So we have 1 this way here again. And then this second division sign, this one, we are changing it to the normal traditional division, like this. Divided by 5 and half. 5 times 1 is 5. So you have 5 over 2 this way. So it has become a bit simple. Then when we were doing the board maths, we came across the law of reciprocity, where you change division to multiplication and then something happens. So we are now changing these divisions to multiplication, and this will become 1 multiplied by, because we are changing division to multiplication, 5 will go up and then 1 will come down this way. Multiplied by, then we come here, we have 1 here. We are changing this division also to multiplication this way. 2 will go up and then 5 will come down. So this is the situation we have. We can go ahead with our cancellation and see the results we have. Of course, this one will cancel this one. This one can also cancel this one. 5 will cancel itself 1. 5 will cancel itself 1. Then the upper part, we have 2 times 1 times 1 times 1. That is 2. And then the denominator, we have 1 multiplied by 1, and that is 1. 2 divided by 1 is 2 as the final answer. Any question about this? This is how you can tackle this question by using this indices law. That anytime you have any subject raised to the power a negative exponent. If you want this negative to go away, just push it from the upper part and bring it down to the lower part. That was what the law was saying. So that is our first solution to our first problem today. Let's go ahead and look at the second one. If there is no question about this one, let's go ahead and look at the second one. Right, so the second one, you have a lot of figures here. And I want you to study the figures. Anytime you see a bracket, or if you see brackets being put together, it means they are multiplying. So let's say this is one bracket, this is another bracket, this is another bracket. Anytime the brackets touch one another, it means you can multiply them together. So we are going to pick each of them, we'll work each of them out, and then whatever results we get, we can then multiply all of them together to find our final results. So look at the question. I'm going to rewrite it somewhere, and then we work it together. After the solution, if you have any question, you can ask to clear your mind. So let me get a fresh page and write a question there so you can follow the solution. So let's start our solution from here. First of all, let me repeat the question here. That if you have 16 divided by 81 raised to the power -1 on 4 multiplied by 32 divided by 2, 4, 3 raised to the power 1 on 5. And then there's another bracket which has 4 divided by 9 raised to the power 1/2. And then we have 3 on 2 all raised to the power 0. Sometimes when you have a question like this, you are likely to use more than one law. If you remember your laws, we did some law 7, whereby I said whenever I have A divided by B to the power -m, I told you that to make this negative go, the law says that bring the denominator up and bring the numerator down. By doing that, the negative sign will go. So that was a law we treated. And we also said that if you have numbers in brackets and there's an exponent, you can share it for them. So finally, we share the m for them, and so we have b raised to the power m and then a raised to the power n. There was a law like this, so you can refer and want to apply that law to this one, because we can see that all the others have positive exponents. It's only this one that is having a negative exponent. So we'll apply this law to this one. Then the others also, we can't leave them like that. We are going to apply law 9. Law 9 says that anytime you have a raised to the power 1 over a certain number, m, law 9 said that open a root sign like this, put the subject A under the square root sign. And then the denominator you have here, you put it this way. So I think this was law 7a. This was law 7b. This was law 9. Okay. So far I've written 3 laws. 1, 2, 3. Then what about, so that one will take care of anything that has 1 over something. So 1 over something, 1 over something, 1 over something. Law 9 will deal with them. What about raise to the power 0? There was another law we did. I've forgotten. I don't know whether it was law 4 or law 5. We said any number raised to the power 0 is the same as 1.
Law 5.
Law 5. Thank you. Let me correct myself here. So that was law 5. That anytime you have any number raised to the power 0, the answer is automatically 1. So if you add this one to this, it means we are going to apply 4 laws. 1, 2, 3, 4, before we can be able to finish this question. And sometimes that is how the questions demand. It demands you to use more than 1 law. Unlike the first one that we use 1 law to solve the problem. This one we are going to use all the 4 laws. So I'll just write this one to just remind you of the laws. I'm now going to apply the laws to treat these 4 brackets we have. And then after that, let's see the answers we have. If you have any question, you can ask. So I need this negative to go away. I'm using law 7a. It means 81 will go up, 16 will come down, and then the negative goes away. So I have 1 over 4. The others, we can repeat them. 32 over 243 raised to the power 1 over 5. Another bracket, 4 over 9 to the power half. The last bracket, 3 over 2 raised to the power 0. So this is our step 1. Step 1, we have used law 7a to take off the negative that was attached to the 1 over 4. Then we proceed. We want to use law 7b, whereby it says we should share the powers for all of them. So we are going to rewrite these as follows. That 81 should stand alone with its power 1 over 4. Divided by 16 should also stand alone with its power 1 over 4. So that is the first bracket. Second bracket, we still keep sharing. 32 will stand alone and have its power as 1 over 5. Divided by 243 will also stand alone with its power as 1 divided by 5. Third bracket, 4 is standing alone with its power 1 on 2. And then the denominator 9 is also standing alone with its power 1 on 2. Then we come to the last bracket. 3 will have its power raised to the power 0. Divided by 2 will also have its power raised to the power 0. And this is the end of step 2. So step 2, what we have actually done is we have shared the powers for them. So if we use law 7a here, we have used 7b also here. Okay. Then we take them one after the other and treat them. Then we try and cast our minds back to the laws we know. And then, of course, a law will come into mind that anytime you have a raised to the power 1 over m, the law says that open a root sign this way, place the subject A inside the root sign, and then the denominator m, just put it somewhere on top here in front of the root sign. And I think we did a couple of examples the other time. So let's use that same principle for what we have. Now, these are the things we have. 81 to the power 1 over 4. How can we write it? This is how we can write it. So we open a root sign like this. We put our 81 there. The denominator is 4. So we put our 4 to sit in front of the root sign this way. We do same to the 16. We open our root sign. We fix our 16 inside the root sign. And then the denominator 4 will sit in front of the root sign. So this is our first bracket. Then second bracket, same. Open our root sign, fix 32 in there, and then the denominator is 5. So it says in front of the root sign. We do same to the denominator, open a root sign, fix in the 243, and then let the denominator 5 be in front of the root sign. That's the end of the second bracket. The third bracket, we do same, open a root sign, fixing the 4, put the 2 in front of the root sign. Denominator, open a root sign, fix the 9, put the 2 in front, close your bracket. Then the last one, we have to use the law that says that any number raised to the power 0 is 1. So once we have 3 raised to the power 0, 3 raised to the power 0 becomes 1, divided by 2 raised to the power 0 also becomes 1. And this is the end of the third step. So this is step 3. So step 3, we have used 2 laws. We have used the law that says 9, law 9, a raised to the power 1 over m equals root of am, and then law 5, a raised to the power 0 is 1. Let's then break them down and finish our calculation. So let's look at it closely now. Now, this is quatic. The other time I showed you, 4 is quatic root. It means what number can you multiply by itself 4 times to get 81? What number can you multiply by itself 4 times to get 81? Now, those who didn't know how we were doing it the other time, I told you that you just use your calculator. When they say, what number can you multiply by itself 4 times to get 81? You can start from 2. On your calculator, you can type 2 times 2 times 2 times 2, 4 times. You see that the results you get, it will not be 81. So it cannot be 2. So from 2, then move to the next number, 3. So you have 3 multiplied by 3 by 3, 4 times 3. When you put this together, you get 81. So it means that the quatic root of 81, the whole of this, the answer is 3. It means that when you multiply 3 by itself 4 times, you will indeed get 81. So our first answer for quatic root of 81, the answer is 3. So you write your 3 divided by, then we come to quatic root of 16. What number can you multiply by itself 4 times to get 16? And I hope you know the number by now. That is 2. When you multiply 2 by itself 4 times, you have 16. So quartic root of 16 is 2. So our second answer is 2. So this is what we have for our first bracket. Then let's look at our second bracket. Our second bracket is 5, which is quintic. It means what number can you multiply by itself 5 times to get 32? Let's try 2. 2 multiplied by 2, multiplied by 2, multiplied by 2, multiplied by 2. 5 times. What do you get? When you put all these together, you have 32. So it means that the quintic root of 32, our answer is 2. Divided by, then again, we want the quintic root of 243, meaning what number can you multiply by itself 5 times to get 243? So we do the same thing with our calculator. 3 multiplied by 3, multiplied by 3, multiplied by 3, multiplied by 3. When you put all these together, you will have 243. It means that the quintic root of 243, the answer is 3. Then we go to the third bracket. The third bracket is square root of 4. This one, you know it already. Square root of 4. Which number can you multiply by itself 2 times to get 4? That is 2. So square root of 4 is 2. Divided by square root of 9. Same. Which number can you multiply by itself 2 times to get 9? And that is 3. So that one also you have 3 as well. And then we have the 1 out of 1 at the last end. So at this point, you have now simplified all the expressions and you now have single numbers in each of the brackets. And I told you that anytime 2 brackets touch one another, it means multiplication, multiply them. So this can be rewritten as 3 out of 2 multiplied by 2 out of 3 multiplied by 2 out of 3 multiplied by 1 out of 1. Then we can simply do our cancellation and end. So definitely 1 and 1 will go. And then 3 will cancel itself 1. It will cancel itself also 1 here. Then 2 will also cancel itself 1. It will cancel itself 1 here. We are done with the cancellation. So finally, we can say at the top here, we have 1 multiplied by 1 multiplied by 2 multiplied by 1. So the numerator is 2. And then we have 1 multiplied by 1 multiplied by 3 multiplied by 1. And that is 3. So it means that finally our answer is 2 over 3. 2 over 3 is our answer from the question we wrote. Any question about the steps we have gone through? Step 1, step 2, step 3, and the final step. Any question about how we were able to solve this indices question by applying the laws? All right, so if there are no questions, let's go and pick. Yes, Gabriel, are you asking a question? I see your microphone on.
Okay, it's fine now. It's fine.
All right. Okay, so let's look at the third one. This was the second question I said, let's solve before we go to the logarithms. Let's pick the third question and we can be sure we have done justice to all the 3 questions. So the third question, I want you to watch it carefully. We are going to use a certain technique to work out the third question. The third question says that we have the cubic. 3 means cubic. Cubic root of 4 multiplied by 1 over the ninth root. The ninth root of 8 multiplied by the 12th root. I'm sure this is the first time you are seeing this indices question in your life. The 12th root of 4 to the power negative 2. And then all has been put to a power of 1 out of 4. Let's see how we can break this question down as we did to I. And I'm sure when we are done with that, you know some of the tricks that I use. So let me recopy the question again here, and then we can solve it. So the first one is the cubic root of 4 multiplied by 1 out of. Then we are now at the ninth root of 8 multiplied by, then we move higher. We now want the 12th root of 4 to the power negative 2. And then all of them are put in a box, which is raised to the power 1 over 4. So there were some laws we learned the other time, which we must apply some of them here. And I want you to help me remember those formulas. There was a law I wrote that when you have A, B raised to the power M, you share the powers for them. So this one becomes A raised to the power M, B raised to the power M. What number did I give to that law? That was law what? Who remembers it?
Law 7.
Law 7. Okay.
Yes.
Right. Okay. So we use this law. So law 7, let me write it, law 7. And then as usual, we also wrote this law we have used. Okay, so somebody has corrected us. That is law 7b. Thank you. So then we also wrote another law which we are writing again. We wrote this one a few moments ago, that anytime you have A raised to the power negative M, is the same as 1 over AM, this way. What name did we give to this law? Those of you have your notes. What number did we give to this law? Okay, let's continue. I just hope you have the laws. So what we do here is
Law 6.
law 6. Okay, so this is law 6. Very good. So we need to keep working inside before we come outside and share the powers for them. So let's kickstart. Now this one, cubic root of 4, we can write it as 4 raised to the power 1 over 3, according to law 9. Law 9 says that if you have A raised to the power 1 over M, it's the same as open a root sign, put A in there, put M outside. And so that's what I'm seeing here. So I'm using law 9 for this one. That if I have cubic root of 4, it's the same as 4 raised to the power 1 over 3. So that when I want to go back here, I'll follow this law. that I'll open the root sign, put in the 4, and then this will be my m. And then you put the m to sit in front like this. So I'm done with this one. Multiplied by 1 out of, I'll do the same thing here. The 9th root of 8, I can write it as 8 raised to the power 1 over 9. Meaning I'm using law 9. That anytime I have m root a, I can come back to a raised to the power 1 over m. Multiplied by, again, this one, I need to do some work here. I need to work the inside first. So in working the inside first, we can write it as 4 to the power -2. But with what we are doing, 12 here means that 1 over 12 when we are using law 9. So this 12 will change and become multiplied by 1 over 12 like this. That is how it's going to turn out to be. That's one way that we can have it. And so all of them are in a square bracket. And then there's 1 over 4 sitting on top. So what we are going to do now is then let's see how we can now break down these numbers into one number. 4, 8, 4. Is there a common number we can use? Yes, there's a common number we can use. And that common number is 2. 4 is the same as 2 raised to the power 2. 8 is the same as 2 raised to the power 3. So instead of 4 and 8, we are going to put in 2 raised to the power 2, 2 raised to the power 3. The intention is to try and put all of them together and not to scatter them. So this 4, I'll write it now as 2 raised to the power 2. But already there's a power there, 1 over 3. So we multiply it by the power we have there, 1 over 3. So we have something like this. Multiplied by the second one, 1 over, now 8 is the same as 2 raised to the power 3. So write it as 2 raised to the power 3. But there's 1 over 9 there already. So we multiply it by 1 out of 9. Then we keep going. The last one is 4 raised to the power -2 times 1 over 12. All we are doing is to change the 4 to look like 2. So 4 is the same as 2 raised to the power 2. But already we have some powers already, so we need to bring them. So it will be multiplied by -2 multiplied by 1 over 12. After that, we put all this in a box. We put all this in a box like this. And then we bring this power here, 1 out of 4. At this point, if you have any question, ask before I continue, because we are done. We are not done yet. Any questions so far from the 3 steps we have written? That we use law 9 to change this one to this. We use the same law 9 to change this 9th root to this. We use the same law 9 to change this one to look like this. After that, I'm saying we need a common number to represent all of them. So I see 4 here, I see 8 here, I see 4 here. Question is, can you write 4 in terms of a lower number like 2? Can you write 8 in terms of a lower number like 2? Yes. If it were to be no, we wouldn't have been able to do that. We'll continue. Yes, Harrison. Let me see whether I need to unmute you. Yeah, so you can unmute yourself now and ask your question.
All right, sir. So the 4, 8, and 4. If there is no number that can break these 3 numbers down, what happens?
So then you continue to work it like that. You continue to work it like that. Yes.
Okay, so instead of breaking the 4, 8, 4 by 2, you can decide to go ahead with the 4, 8, 4.
Yes, exactly.
Okay.
Exactly. You can decide to go ahead with it, and you still have the same results. All right, so good. That was a good question. So now let's try and simplify things here now. Let's make things simple. And so let me tidy this place up. Then I can come here and write it for you to see what is happening. Let's see whether some cancellation can help us. I see 2, I see 3, they cannot cancel. So what do I do? I'll just maintain it. 2 times 1 is 2. So this one can be written as 2 to the power 2 over 3, because there's nothing I can do here. No cancellation is possible. What about the second one? The second one, I see some possibility. 3 will cancel itself 1. 3 will go into 9, 3. So this whole thing will reduce to times 1 divided by 2 raised to the power 1 over 3. So the power has reduced. Multiplied by, then I come to this side. Some cancellation can work. 2 will cancel itself 1. 2 will go into 12, 6. 2 will cancel itself 1 again. 2 will go into 6, 3. So it means that this whole bulky thing has reduced to 2 whole number. The top, I see 1, -1, and 1. So 1 multiplied by -1 and 1, you have -1. So you have -1 divided by 3. And all of them are still in the box. And then you have the power 1 over 4 outside the box. Yes, Harrison, go ahead.
Yes, sir, please. You use the 2 to cancel 12.
Yes.
The first 2 to the power 2. The power 2, you use it to cancel 12.
Exactly.
And you had 6.
Yes.
And then you came down to use the -2.
Yes.
To cancel 6.
Yes.
Wouldn't the negative have effect on the 6?
No, the negative will stay there. The negative
to stay at the top there.
Yeah, it will still stay at the top there.
Okay.
It will still stay at the top there. It will not have effect on the 3. So because
so eventually
eventually
the negative will affect the 1 over 3, the exponent 1 over 3 will carry the negative eventually.
Exactly so. Exactly so. Like you are seeing, that is why it is carrying it. Right, good question. So let's proceed. If you are not clear in your mind, please ask before we end. So now we want to tidy things up. Our wish is that everything will be a straight thing. But we are seeing some denominator here. We need to look for a law that can push this one up for us. Once we get it up, then we get a uniform line, then we can go ahead and work. And there's a law that can help us do that. You know it, let me remind you. There's a law that says that if you have a raised to the power -1 m is the same as 1 over am. This same thing, you can also turn it and see that 1 over am is the same as a raised to the power negative m. In other words, if you have a fraction like 1 over something, and you don't want to keep it like a fraction, but you want to keep it as a whole number like this, all you do is you target the exponent. If it is down and is going up, it becomes negative. If it is up and is coming down, it becomes negative. So the moment you change direction, then you have to apply the negative sign. That's what we are seeing here. Now it is up, it's negative. When it comes down, it becomes positive. Now it is down, positive. When it moves up, it becomes negative. So we are going to apply this law to this one here so we can have a uniform writing. And then we can go ahead and simplify. So we still repeat this one, 2 whole number, 2 on 3, multiplied by, now we are moving this one up. So the exponent will go negative according to law 9. So write this one to us, 2 raised to the power, instead of positive 1 over 3 becomes negative 1 over 3 because of the application of law 9, which says that if you have a raised to the power negative m is the same as 1 over am. So our a is the 2. Our m is the 1 over 3. So once they are down here and they are moving up, then they should become like this. And that's why I've written it this way. Then we have this here already, 2 raised to the power negative 1 over 3. All of them are in a box. And then the power sitting on top of the box is 1 over 4. Any question here before I continue? This is how we can tidy it up. Now we have all of them on a straight line. And we can proceed with the rest. The moment you see the same base, 2, 2, 2, and you see multiplication, then the first law should come into your mind. The first law says that a raised to the power m multiplied by a raised to the power n is equal to a raised to the power m plus n. So the first law says that anytime you have the same number serving as the base, 2, 2, 2, and then you have multiplication in between them, all you do is that just go in for the powers and then add the powers up. That's what the first law says. So at this point, we need to apply the first law and get the results done. So I'll continue the solution up here so you can appreciate what we have done so far. I'll write it boldly now. So we have 2 raised to the power 2 over 3, like this, multiplied by 2 raised to the power negative 1 out of 3, multiplied by 2 raised to the power another negative 1 out of 3. And all of them are in a box, raised to the power 1 out of 4. So I want to use the first law now to finish up. First law says that a raised to the power m multiplied by a raised to the power n will give me a raised to the power m plus n. So same thing here. So I have this one is equal to a big 2 like this, raised to the power. Now we are adding the powers. 2/3 plus, look at the sign here, minus, so plus, minus 1/3 plus, look at the sign here to minus, minus 1/3, all in a box, raised to the power 1/4. You and I know that anytime positive and negative meet together, it becomes negative. In other words, we can rewrite this one again as 2 raised to the power 2/3 minus 1/3 minus 1/3 raised to the power 1/4. So we have a fraction here, 2/3 minus 1/3 minus 1/3. Let's find the LCM. If you do the LCM, you have 3. 3 here, 1. 1 times 2, you have 2. 3 here, 1. 1 multiplied by 1, you have 1. 3 here, 1. 1 multiplied by 1, you have 1. So look at it. 2 minus 1 will give you 0. 0/3. 0/3 is the same as 0. So it means that from here, we have now reduced everything to 2 raised to the power 0. And there is a power outside. How do we conclude? There was a third law I gave you, which says that if you have A with a power inside M, and then there's a bracket, and another power N comes, all you do is to multiply the two powers. That's the third law. So when you multiply the two powers, your result becomes A raised to the power M times N. And then finally you have A raised to the power Mn. So we are going to apply the third law to this one. I see a power inside the bracket, and I see a power outside the bracket. So we apply the third law. And then finally we have 2 raised to the power 0 multiplied by 1/4. And this will still give you 2 raised to the power 0. And then we then end with the law we know already, which says that A raised to the power 0 is 1. Therefore, our final answer is 1, according to this law, that any number raised to the power 0 is 1. And that is the end of the solution of this complex question. Any question about the solution before we start the logarithms? Any question about the third solution of the indices we have done today? Okay, so I presume everybody is fine. Yes, Gabriel.
So say, are we supposed to learn all the 10 laws? Like, memorize all the 10 laws? Or you add it to the exams paper?
Oh, Gabriel, what are you saying? You are supposed to memorize it. You are supposed to memorize it. You are solving a problem. I'm giving you a problem to solve. So in the business world, we say you have to use something we call prior knowledge. Prior knowledge. Some people call it experience. Some people call it experience, but it is prior knowledge. So you need to memorize the 10 laws. That's part of the work of you as a student. because I also memorize it and I'm able to quote it when I see a problem. So once you work the problems I've given you, it will come naturally. Without the laws, you cannot work. You cannot work to get the results. It is guiding all the breaking down of the system. Can you imagine without the laws, how would we have been able to solve a problem like this that solve cubic root of 4 times the ninth root of 8 multiplied by the 12th root of 4 to the power negative 2, all raised to the power 1/4. We cannot be able to solve this if we don't use the laws. So you are duty bound. You have to learn the laws and then use them appropriately. You see that when you are solving the questions will force you to go and recall the laws. It's not like you just memorize it naturally, but the kind of question you see will make you go and look at the laws, that which one can work. For instance, look at a question like this. Now they are saying you should solve 2 raised to the power x equals 64. So find x. How do you work such a question? The law says that before you can compare two things, make sure you break 2 down. Make sure you break 64 down to look like 2. If you are not able to break 64 down to look like 2, you cannot do anything. So you ask yourself, how can you break down 64? You just pick your calculator and see the number of times you can multiply 2 to get 64. So you keep doing it. You multiply 2 by 2 on your calculator. You get 4. 4 is not 64. So you need to keep going. You multiply by another 2. You get 8. You still haven't got in there. Multiply by another 2. You have 16. You still haven't got in there. Multiply by another 2. You have 32. You still haven't got in there. Multiply by another 2, where 32 times 2 will give you 64. So then it really means that if you want to break down 64 to look like 2, you need 1, 2, 3, 4, 5, 6 of them. In other words, 64 is the same as 2 raised to the power 6. So in the indices, once the bases are the same, it means the powers are also the same. Therefore, x is equal to 6. Without the loss of indices, how would you be able to solve for x like this? It wouldn't. You need to break it down with the loss. So as you move on, I have several questions for you. If you have time, just go through them. And the more you go through the questions, the more you are able to get the loss working at the end of the day. That was a good question. Any other question before I move to the logarithms? Okay,
So the examples we can't find it on the LMS, the one you are showing us.
yes. The other time, I think somebody was complaining to me that it looks as if I was using a different slide. This is for your class. And so what I will do is, class rep, I will send you this one as well. I don't know where the mishap is coming from. Maybe I have to pull down the one on the LMS and then push this one there. And this is the one I used last year. So I'll push it immediately. The class is done. I'll push it to the class rep for you to have the questions, because you need the questions to practice and then get used to the results. Any other question before we move to the logarithms? Okay, so let's move on. Today we have started in a difficult way. Let's continue the difficulty. to the next set of laws, which are also very important in business. And so I want to write them out for you like I did for this one. I have a fresh page now. Let's do the laws of indices, laws of logarithms, sorry. Laws of logarithms. Right. So these are also laws that help us to break down complex systems. It helps us to break down complex systems. And so there are laws. Yes, Harrison.
Yes, sir. Please, I want to ask, the indices and logarithm, are they related or they are different?
Yes, that's a good question. They are related.
Okay.
Yes, they are related. So let me put it in a simple way for you. Whilst we use indices, to break down simple systems, we use logarithms or logs to break down complex systems. So where is the relationship? The relationship is that we move from complex to simple. And sometimes we can move from simple to complex. That is how life is. Sometimes we move from complex to simple, or we move from simple to complex. So that is where they are related. And in this real life that we have, you can't design a system whereby the system is only doing complex things, or the system is only doing simple things. You need the two together to work. You need some parts to be simple. You need some parts to be complex. It's like a moving car. When the car is moving, the seats, the car seats, the dashboard, probably the sound system you are playing, they look so simple because they are not actually doing any work in terms of movement. They are just there. You are on the seat driving. The dashboard is in front of you. And then the sound system is also in front of you. But where are the complex systems? The complex systems are, now look at the way the engine is running, the way the engine works. That's a complex system. Look at how the speakers are able to blast the music or the audio. That's a complex system. So all I'm trying to say is that you need simple systems and complex systems in a holistic system. While some are acting in a simple manner, some are also working in a complex manner, then at the end of the day, you may have the optimal resource that you want. Can you imagine when you are driving and the seat is also moving up and down? You wouldn't be comfortable. Can you imagine driving and the dashboard is also not static? It's mobile. It's moving back and forth. You wouldn't have optimal driving experience. Okay. So they are related. And this is how they are related. You often hear that there is log and there is anti-log. Log and anti-log. So log, complex. Anti-log, simple. And this is where you have the indices. Okay, so somebody will say they are opposite. They are opposite to each other. Simplicity is opposite to complexity, or complexity is opposite to simplicity. But we don't use them in isolation. We use them together. You need simplicity and complexity to have an optimal system running. So that is how they are related. Now let's look at the laws. Let's look at the laws. It has about 6 laws. And the laws also help us to work complex expressions that come our way to have better results or a good result. And so let's write the first law and explain. Now, the first law says that anytime you have log A, like this, and then X is sitting on log A, and then Y is also sitting on log A. Now, this one is association. So log A, watch it, log A, log A. Log A, don't look at it as abstract, is serving as a platform. So log A is like a platform. If it were to be a building, it may be the floor of the building. So that's log A. So now you see log A, log A. So X is standing on the platform of log A. Y is standing on the platform of log A. The sign in between them is addition. Addition means agreement. Okay, it means agreement. So when X and Y agree on the same floor of log A, it means they can work together. So the result is that when X and Y are on the same floor, they can work together. And so their efforts are multiplied. So you have X times Y. So efforts of X and efforts of Y are multiplied together. So the law says that anytime X agrees with Y, the result is multiply the two quantities to get X, Y on the same floor of log A. So what is making this formula bulky is this log A you are seeing here. That is what is making the formula bulky. But it doesn't really add any substance to the individuals. It's the same thing. Log A, log A, log A, same floor. The actual operation is that X is agreeing with Y. So they will multiply. You have XY. That's the first law. Let me give you an example of how it works. So if I have this, so this is an example. If I have log 2, and then the number is 6 here, plus log 2, the number is 3 here. How am I getting the results? The law says that I should look at the floor. So log 2, same floor. So I repeat, same floor, log 2. What is the actual operation? 6 is agreeing with 3. 6 plus 3. So they will multiply. So you have 6 multiplying 3. And then the final answer will be log 2, 6 multiplied by 3, 18. And indeed, it works. If your effort alone is 6 and somebody's effort alone is 3, normally when you combine your efforts, you have a greater effort. So we say 18 is greater than 3, 18 is greater than 6 because the two forces has been combined together and there's a greater force of 18. Yes, Harrison, I saw your hand up.
Yes, sir. All right, sir. So please, if the log A, we can call it a platform, common platform. Is there a name for the X and Y?
Yes, so that was what I said. I said individuals on the platform.
Okay.
Yes, individuals on the platform. So since most of you are adults, let me use marriage. So if you have a trustworthy husband and a trustworthy wife, and none of them is cheating on one another, and all of them are playing their roles, they make progress, they make better progress than they staying individually. That is how it works, that the combined effort of two good people should give a greater results. So the common platform you are seeing can be anything. It can be marriage, it can be business, it can be education, it can be anything that is good or that brings about progress. Anything that brings about progress, when you combine your effort in it, you have a greater results. And that's what the 18 is telling us, that 18 is greater than 3, 18 is greater than 6 because 6 and 3 combine their efforts. And then the net effect of the effort is 18. It wasn't 6 plus 3. It went beyond that. And sometimes it happens. You may have some level of effort. Somebody too may have some level of effort. If you combine, you get a greater effort that goes beyond the two of you. And that is what the law says. That if you have log A x plus log A y, you have log A xy, where the xy will always be greater than the x and the y. Now there's a counter law, which is law 2. Again, this time the same platform, log A, x is still on the platform, but this time it is minus log A again and y. Minus means disagreement. So if you have two people on the same platform and they are disagreeing, you don't expect them to associate. So they can't multiply. They will rather do what? Divide. They will divide their efforts. So the results here will be log A, x will stay up, y will stay down. They can't be on the same level. X is looking elsewhere, y is looking elsewhere. They can't both look in the same direction like we had in the first one. And let's see whether their effort will increase or decrease. Example, if you have log A, 6, the same 6, minus log, 2, log 2, 6, minus log 2, the same 3. Okay. Same people again. Let's look at their efforts now. The law says that because they are not agreeing, they will look at different directions. So 6 will stay on top, 3 will stay down. When you divide, 3 will be here 1, 2 will be here 2. Finally, it becomes log 2, 2. Now look at what is happening now. Initially, we have an effort of 6. We have an effort of 3, or energy of 3. So let's say this is marriage. The initial efforts are okay. Now there is mistrust, and so there is confusion. Look at the resultant effects. Now the combined effort has reduced drastically, far below their individual energies they had from the beginning. And that is what the law says, that anytime there is disagreement, it means the combined effort will be little as compared to the 18 we had here. Same people, when they agreed, the results was 18. But when the disagreement came in, the combined effort has reduced to 2. That is the second law, that log AX minus log AY will give you log AX divided by Y. That is law 2. And this takes us to law 3. I told you there are 6 of them. So let's quickly look at the rest. Law 3 is coming in a different structure, unlike law 1 and law 2. Now, this is what law 3 is saying, that if you have log AX, meaning X on a certain platform, and then you have N on top. The third law says that we don't entertain any form of index or power or exponent in this law. Anytime you see it, you have to push it back. You have to push it back. Okay, let's see how it works. We don't entertain powers or exponents or indices in logarithms. So once you see something like this, it's a picture of like you seated in a car. Okay, you seated in a car, and then you are carrying a load on top of your head. Let's say you are in a commercial vehicle. You are seated, and then you are carrying your load. It doesn't look natural. I'm sure anybody close to you say, no, 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 no. You can put your load either on your lap or you put it on the floor. That is the scenario we are seeing here. X is seated on this platform and still carrying a load. So we need to have a way of offloading this load here. And the only way to offload is to just bring it to the back of the platform. So this one is going to be rewritten as N log AX. That's the law. The law says that anytime X carries anything, just push it to the back of the log. Let's look at a numerical example. So example, if I have log 2x raised to the power 6. Law 3 says that we do not entertain powers in logarithms. So what you do is this 6 will have to find its way to the back of the platform. And so we rewrite this one as 6 log 2x. And this one becomes natural. That at least your load is at the back of the vehicle or underneath the vehicle or whatever, or on your lap. So we have 6 log 2x. That is law 3. Any question before I move to law 4? Law 1, any question on law 1? Any question on law 2? Any question on law 3 before we move to law 4? Okay, so let's proceed to law 4. Now, law 4 also have a different structure. It says that log A, the answer is automatically 1. Yes, Harrison.
Yes, sir. Please, any example on this one, log 3, the log 3.
Yes, so I did it. Didn't you see it?
I didn't see it, sir.
Oh, where did I put this thing? Okay, let me look for it for you. Yes, this is the example sorry, let me go back. I was trying to magnify it for you. Take the example I did. I said, if you have this log 2 x raised to the power 6, we don't entertain powers in logarithms. So we throw
Yes,
this
sir.
one away to come to the back. And that's the results we had. 6 log 2x.
Okay.
Have
Okay,
you
sir.
seen
Thank you.
it? Very
Thank
good.
you, sir.
Good. So we are now at law 4. Law 4 says log AA is 1. So it's like you standing on the floor. Okay. You are standing on the floor, walking this way. And probably somebody has put some soapy water here on the tiles. You didn't see. So once your friction reduces, it slips you and then you fall down from your vertical position. When it happens that way, it means you and the floor have become one. And that is the law. It says anytime you look like the floor, this is you. You are A. The floor too is log A. So anytime you look alike like this, it means you become one. And so once you slip and you fall down, you are just flat like the floor. That's what the law is saying, that anytime you have two numbers in which the subject number here and the base number here are the same, it means they have become one. So automatically the result is one. Example, if I say solve log 50, 50, automatically write 1 for me. You don't solve anything because the base number and the subject number has become the same. So they are 1. So automatically the result is 1. If you have log 1,000, once they are the same, automatically your answer becomes 1. So that is what law 4 is saying, that anytime the base number and the subject number are the same, you have 1. Law 5. Law 5 says that anytime your subject number becomes 1, automatically the answer is 0. Log of the number 1 is completely 0. Because at the end of the day, if you want this log to live here, it means A will also have to live. Log and A, they have to live at the same time. And how do they live? It is something that most people don't know. Assuming we want this log and A to go so that one can stand alone, this is what happens. If you have log A1 and you want the log to live, you want this log to live, you want this A to live, this is what is going to happen. The moment this log leaves, the moment this log makes any attempt to leave, A will also go and carry the 0 here. So you have 1 equals A carrying the 0, because A and the 0 cannot be on the same level. A is going to push 0 up. So you have A raised to the power 0. And you know that any number or letter raised to the power 0, the answer is 1. That is why log 1 is always 0. Because anything you leave here will have to go and carry the 0 to change it back to 1. So the log of 1 is always 0. Let me give you some examples. Example, log 5, 1. The answer is 0. Log 20, 1. The answer is 0. The moment you see 1 as the subject, straight away, the answer becomes 0. That is law 5. Then we go to law 6, which I can write up here. Now law 6 also comes this way. If you have log A x is equal to log A 5. The law says that check the platforms. Are they the same? Log A, log A. If they are the same, the law says that just cancel the platforms. And then therefore, we say that x is equal to 5 as our answer. So anytime you have two platforms, one at the left, one at the right, so far as they are the same, the law says that just cancel them and then equate the numbers left, the number on the left and then the number on the right. Just equate them to have your answer. And that is law 6. Now, law 7 is very interesting. Law 7 is an interesting law, and I want to take my time and break it down for you. So let me clean the space, and then I can use the space to do law 7, and then we'll end with law 8. And then if you have any question, you can ask. Maybe we can solve one question before our time will be up on this one. So law 7, this is law 7. It says when you have log A, the result is as follows. The result is log C B divided by log C A. So this is a relationship between her here. Now let's say B is a guy, A is a lady, and then there's a confusion in their relationship. When there's a confusion in their relationship, then you need a third party called C. If you take A, B, C, A is a friend to C. B is also a friend to C. So both of them have C as their friend. So when there's a confusion between the two of them, like it was done in the olden days, C as a betweener will come and talk to B to soften his stance. And then the same C will also go and talk to A to soften his stance. When both B and A listen to C, it means that the relationship can bounce back. Matter is settled. So that is the first law. That's the 7th law, sorry. On the other hand, law 8 also says that the same A and B, if they have confusion, and then C comes to talk to them, and there is no agreement, it means that B will go his way, and then A will also go his way. There's no agreement. So the two laws are interrelated. Whilst the first part, the betweener is able to settle the two of them and there's agreement. The second one, there's no agreement. That's why you're not seeing the betweener in the eighth law. The C is lost because none of them listen to C. So C is gone. So they are also going their separate ways. Now, numerically, how do we apply this one? Let me give you an example for you to understand the law. So, example, if I give you this question that solve log 927, how are you going to do that? Log to base 927. These are huge numbers. So what first of all we do is that we need to apply law 7, meaning that when we pick our log 927, we ask ourselves, what number is common between 9 and 27? What number is common between them? And I'm sure you know that 3 is common to 9 and 27. So 3 can convince 9, 3 can convince 27. Why? Because 3 can really divide the two of them without any remainder. So we can rewrite this one as log, according to the law, log 3, 27 divided by log 3, 9. Let's see whether 3 can do the job. The next thing is that how can we let 27 look like 3? After all, that is the problem 3 has come to solve. 3 wants 27 to think like 3. And 3 also wants 9 to think like 3. Once that is done, then we can have a solution. So you realize that 27 as a number is the same as 3 multiplied by 3 multiplied by 3, which we can write as 3 raised to the power 3. 9 is also the same as 3 multiplied by 3, which we can also write as 3 raised to the power 2. So what we do here now is we now want them to think like 3. So we write this one as log 3, then 27 is the same as 3 raised to the power 3 divided by log 3, 3 raised to the power 2. But from what we have learned today, we don't entertain powers or indices in logarithms. And so law 3 told us that when we have a situation like that, we should throw the index to the back of the log. So this will now become 3 log 3, 3 divided by 2 log 3, 3. 3 log 3, 3 divided by 2 log 3, 3. We've also learned another law today. And the law was that anytime you have log AA, the answer is 1. So we are having log 3, 3, log 3, 3, meaning we can rewrite this one as 3 multiplied by log 3, 3 is 1. And then 2 multiplied by log 3, 3 is also 1. Finally, our answer becomes 3 divided by 2. And that is how the law 7 works. It means once you are able to get a number that can divide 9 without a remainder, divide 27 without a remainder, you are sure to get the final answer by breaking it down. But law 8 says that if there is no familiar number, you can't do anything. For instance, if I say solve log 5 7 for me. I need an answer. What will be the answer? 5 and 7, there's no number that is familiar to them. Because there's no number that is familiar to them, your final answer will be that then log 7 should continue to stay up. And then log 5 should also continue to stay down. And this becomes your final answer because there's nothing you can do. There's no agreement. So the answer is left this way. And that is law 8. And that is the last law I wanted to explain to you today. Any question about all the laws we have done? Yes, Joseph.
Yes, sir. Thank you, sir. So, sir, the law 3.
Okay, let me go.
Can you please take a different example and then let's see if,
Okay, so I'm back to the law 3. So let's pick a different example for the law 3. So example, if I have log 5, 7 raised to the power 3, log 5, 7 raised to the power 3. Law 3 says that you cannot carry any number as a power once you are seated on the floor. So once we have a floor of log 5 and 7 is seated on the floor of log 5, we cannot carry 3. So 3 will have to come to the back of the log. So when we are rewriting the solution for this, it means we are throwing this 3 back. So we have 3 log 5, 7 as our answer. So this will be the answer. We can't go beyond this. We've been able to offload the 3 to the other side. Is it clear, Joseph?
Yes, sir. I'm okay now, sir. Thank you.
Right. Good question. Any other question on the laws before I pick an example? Any other question? Okay, so I still presume you are okay now. With a few minutes we have, it's about 20 minutes or so. Let's pick an example and apply the laws that we know. So I'll pick an example which you'll be okay with. So there are several questions I have, and thankfully some of them there are answers. So once you work it, you can just cross-check with the answers there whether you are right or wrong. So I'll try and see whether we can solve about 2 of them before we end the session today. So I will not pick simple ones. Let me pick some difficult ones that can help us apply some of the laws we know from the 8 laws I have written. So I'll pick from these examples that I'm having. Let me pick this one. Let me pick N. Let's do this one as our first question. And then once we are done, we can also pick this as our second question. But before that, let's have an idea of the expected answers we are supposed to get. Looking at the N from the possible answers I have here, looking at N, where is N? Yeah, N is here. So it means that N, we are required to get 44 after working. And then the O that we also want to work at the end of the day, we should have 2 as our answer, because these are the answers. These are the answer columns. So we need to get 44 and 2. Once we don't get them, it means something have gone wrong. We need to go back and fix them. So let's start. Let's pick the first one. Let me write it boldly somewhere here, and then we can solve it together. So I write the question for N. I write the question for N. So N, the question was solve 2 log 5, 6 to 5 plus 27 log 3, and then there's cubic root of 81. Cubic root of 81. So let's see how we can apply the laws to solve this problem. The first thing you should always try and do is that when you see the base number here, 5 and 625, just like the betweener thing we were doing, see whether you can write the 625 in terms of 5. That's the first thing you check. You check whether the 2 numbers can agree. Okay. So you pick your calculator, you want 625. You pick 5. You multiply 5 by 5. That'll give you 25. We haven't gotten there. You multiply by another 5. You have 125. We still haven't gotten there. You multiply by another 5. And this one will give you 625. Okay. Meaning 625 is the same as 5 raised to the power 4. So that's the first thing we can do. We are going to change the 625 and write it as 5 raised to the power 4. And then we continue. So let's write it now. We can rewrite this one as 2 log 5. 625 is the same as 5 raised to the power 4 plus, we have our 27 log 3, and then this cubic root of 81. Remember when we were doing the indices and we're using the law 9. The law 9 said a raised to the power 1 over m is equal to, you open a root sign like this, you put the a in there, and then the m sits in front here. So this one too, we can rewrite this one as 81 raised to the power 1 over 3. 81 raised to the power 1 over 3. So we avoid this root sign we are seeing here, right? So that would be our step 1. And then step 2, we start applying the laws. We are seeing 5 carrying 4, and it cannot be, because the law 3 says that anytime you have log a x n, throw the n outside the platform, so it becomes n log ax. That's what we are exactly doing here. So 4 is being thrown to the back of the log, but there is 2 there already. So that 2 will stay, that 4 will come and join, then have log 5 this way, plus this 27 is also still there. We are throwing away this 1 over 3 to come and join. So multiplied by 1 on 3 log 3 81. Yes, Harrison, you can ask your question.
Yes, sir. Please, the initial, this one, the 4 that we threw to the bag of 2 log, the position of the 4, won't the 4 come before, won't the 4 multiply the 2 log?
Yes, so because it's multiplication, it doesn't matter. Any of them can agree to change position.
So that the initial 2 log, has now become 4 log.
No, the initial 2 log, the 2 is
So the
separate
4,
from the log.
okay,
The 2 is separate from the log. The 2 is just standing alone. It's just at the back. Okay, it's at
okay.
the back. So let's
So
say it's go ahead.
if it is at the back, and then we are lowering the load the 5 is carrying, we want to break it down, then it should go to the back of the 2.
No, don't worry about that. So it's like a classroom.
Okay.
It's like a classroom. So let's say an old student is seated somewhere, and then a new student comes. Maybe the old
Okay.
student crowd wants to change his sitting position and go and sit somewhere. So in terms of arrangement, this is all I'm trying to say. 2 multiplied by 4, 4 multiplied by 2.
They are the same.
Very good. You have the same results.
Okay. Thank you. That's what
But I still can, if you want as a class, we can still follow your logic as a class. So as a class, let's go by it this way. That at the end of the day, 2 is still at its position. It is the 4 we are throwing to come and join the 2. So the 4 will rather come somewhere here so it doesn't displace the 2. So we can accept it as a class, as a convention, that anytime we throw a number, the existing number should stay where they are. It is the new number that should really come in front, which is okay. So we have this one as well. Harrison, did you finish with your question? Are you okay? Or what? There was
Yes,
a
I'm
follow-up.
okay. I just wanted to follow the sequence.
Very good. No, very, very necessary. I mean, I agree with you perfectly. So then at this step, if I'm going to follow the logic, then I'll change this side also. Let's allow the 27 to be at its position, and then the 1/3 that is joining should come somewhere here. So at this point, let's try and simplify what we have. 4 multiplied by 2, you have 8. Then we have our log 5 plus. Then this side we can do some cancellation. So 3 will cancel itself 1. 3 will go into 27, 9. So that has reduced to 9 log 3, 81. This 81 seems so big, we need to do something about. So the question is, can 3 divide 81 without any remainder? We try with our calculator, so we keep trying. So 3 multiplied by 3 is 9. We haven't gotten there. Multiplied by 3 is 27. We haven't gotten there. Multiplied by another 3 will give us 81. So it means that 81 is the same as 3 raised to the power 4. Harrison, you can ask your question. You have 8 log.
I wanted to ask, but I think I have withdrawn.
Okay. All right.
I wanted to ask if the 3, the 1/3, the 3 you used to cancel the 27.
Yes.
I wanted to ask if you can equally use it to cancel 81, but I have withdrawn.
Oh, no. You can't use it to cancel 81. Yes. Because it is outside the platform.
Yes, that is fine. Thank you, sir.
The 81 is sitting on the platform, but the 27 is outside the platform. Yes,
sir. Thank you.
Right. Joseph, I see your hand up.
Yes, sir. So, sir, I want you to go back to where the root sign is, the 81.
Okay.
The three, yeah, yeah, sure. So, uh, I remember you said something like the quadratic root and
Cubic.
a cubic root. So I don't know whether you can straight away do it in that way when you get to this point, like the 3 times 3 times 3 times 3, that will give us 81. So
Uh-huh.
3 will multiply is 4,
Uh-huh.
get 81. So straight away, I think that whole statement will be log 27 log 3 to the power 4, and then 27 log 3, and then 3 to the power 4. I don't know whether you
No, it,
understand.
it cannot happen because look at this cubic. This one is here. What you are changing is the inside. So it would have been cubic root like this of what your 3 to the power 4. Are you talking about this? Yes.
Mm,
Joseph. Aha. So you see that we will have a problem. In fact, our objective here was to see that how can we take this thing off? Well, this thing is bringing a problem. How can we take it off? And then I just give you a reminder that when you look at the law 9 of indices, where we had a raised to the power 1 over m, where we opened a root sign like this, and then the a was inside, and then the m was outside. That was
yes.
what I did for this one. That if I want to get rid of this, so that I'll write it like a number raised to the power a certain fraction. How am I going to do it? So I just lined it up. I brought this one here, this one like this, 81, and then the 3 is sitting here. And my question is that how can I write it to look like this one?
Oh, okay.
So, so then I wrote my 81. And then here is this m. The m is 1 over. So that's the 3. So then 1 over 3. That was how come I was able to do it and write it as 81 to the power 1 over 3. So that this
Okay.
sign will go away. Aha. So
Yes,
the
sir.
fact that, yes, I like your question. The fact that we are doing logarithms doesn't mean you cannot apply indices law. You can apply indices law whilst we are doing logarithms.
Okay, sir. All right.
That is why your question is good. Your question has come at the right time. Yes, Harrison.
Okay,
Thank
so
you.
back to that question I asked, whether you could use 3 to cancel 81. So
Yeah.
it means that the 20 you were able to use 3 to cancel 27 because the 27 it's a number on its own.
Yes,
But
that
the
is
log,
outside.
yes,
That is
outside, but the
outside.
log,
Yes.
yes, but the log 81, log
Mhm.
381 is also a different definition on its own.
So yeah, so Harrison, let me create this picture for you. Now,
Yeah.
this is our classroom. We are here. We are learning in our classroom. Okay. And then there is somebody standing outside this way. If we don't open the door, can the person come?
No, sir.
Exactly. So that's what is happening here. The
Okay.
moment you come at the back of the lock, unless the lock opens you, you cannot.
Opens you. Okay.
Yes, you cannot. You still stay outside.
Okay. I get it.
So that's why, yes, that is why we were doing that cancellation there.
All
Right.
right, sir. Thank you.
So very good. So here, like I was doing that, can we break 81 to look like 3 to make life simple for us? That was what I was trying here. And I saw that 3 times itself 4 times will give us 81. So then we rewrite the 81 as 3 raised to the power 4. The moment we do that, we have created another trouble. Another trouble because this 4 is not supposed to be here. So we have to send it back to where it belongs. So then we have 8 log 5, 5 this way, plus. Then this 4 is being thrown back. So we have 4 multiplied by 9 log 3, 3. Okay. Then we tidy it up. So we have 8 log 5, 5. plus 4 times 9 is 36. So we have 36 log 3, 3. At this point, we are concluding. At this point, we have log 5, 5, log 3, 3. Then we remember the law that says that whenever you have same base, same subject number, the answer is 1. Log AA is 1. So log 5, 5 same will be 1. Log 3, 3 same will be 1. So we have 8 multiplied by 1 plus 36 multiplied by 1. 8 multiplied by 1 is 8. 36 multiplied by 1 is 36. 8 plus 36, you will have 44 as the final answer. That is why the answer to that question you are seeing here, you are seeing 44 being recorded here for this question. That the final answer to this is 44 after going through all the steps. So I'm afraid our time is up. Left it about 3 minutes. Any last question before we conclude? I'll make sure next week, God willing, we'll look at the any question about the solution we have. Okay, so if you ask me, how many laws did we use? How many laws did we use in solving this problem? These are the laws I remember we use. 1, we use the law 9 of indices as our first law. And then secondly, yes, Harrison.
Yes, sir. The solution you made, have you cleaned it? I wanted to. The solution.
No, I've not cleaned it. It's here. Yeah, it's here.
I'm not. I think. Okay, sir, please can you let me look at it and then. Okay, I want to. Okay, thank you, sir.
Yeah, so there's the. Are you okay now? All right. So then we use also the third law, which says that log A x n. It means you have to throw the n outside. N log A x. And then finally, we use the law log A is equal to 1 in concluding our solution. Log 5, 5, log 3, 3 is equal to 1. So these were the 3 laws we used for this question. On that note, since our time is up, I want to thank you for your participation. And I hope once I drop this document for you, you look at the rest of the questions and see whether you can try your hands on them. Like I promised, I'm sending it straight away to the class rep to mount it on your platform. I wish you a good week, and officially the class is ended for today.
All right. Thank you very much, sir.
Thank you.
Thank you, sir.
Constraint, please, I need my school fees. Please kindly inform your people. I need my school fees.
So guys,
Fees paid are not refundable.
Roland.
Yes, our
Co-host muted everyone. The meeting will not hear.